So we have been talking about that steady state conduction, and now we are going to look at two-dimensional heat transfer, right? And along with that, we would also look at transient heat transfer. Okay. Now, before moving on to this discussion, how we can look at this steady state conduction in 2 dimension or 3 dimension, or let's say if you involve time as well, there are few very fundamental things about engineering systems. If you want to look at analysis of any system, or let's say design of any system, there are 3 approaches, and those 3 approaches include computation, where you can use the numerical techniques, or you can solve them by analytical techniques, or you can go for experiments. So there are 3 generalized methods to investigate any system's performance. Okay. Now, till this point in this course, we have been talking about the analytical approach. Okay, we have been formulating those ordinary differential equations. We have been solving that using some boundary conditions. We have been looking at their solutions, different forms. Now, from this point onwards, let's say for the next 2 weeks, I would be looking at the numerical approach only. Okay. Now, what do you mean by numerical approach? That you would not have any functional form of temperature. Functional form of temperature, like you plug the value of x, or you plug the value of y, or let's say time, and you get the solution. This would not happen. Okay. Now, numerical techniques means, obviously we are not going to perform the experiments. This is not the lab course, right? So you can perform the experiments once you go into the heat transfer lab. But now this is about numerical technique. Okay. Now, what do you mean by numerical technique? You might have heard about this Taylor series, a very well known thing. Now, what do you mean by that? Now, can you see it? Okay. For example, if you know the value at x1, and through that value you want to find out value at x2, let's say. What does that mean? For example, this is y1 and this is y2. If I ask you how you can approximate the value of x2, sorry, the value of y2 at x2 point using this information, can you understand my question? My question is, again, I would repeat that if you have some previous information and you want to have some information which is not known to you, okay, so what I can write is, I can say that this y2 can be approximated as y1 plus, let's say y is a function of x, plus partial f by partial x, x2 minus x1, plus partial square f by partial x square, x2 minus x1 square over 2 factorial, and you can just have many more terms, isn't it? So this is the Taylor series. Now, my point is that you want to approximate the function value at the next point when you have the information at the previous point and you know partial f by partial x, the delta term, the derivative term. Okay. Now, for example, I put it this way. Instead of giving these nodes as the names like x1 and x2, what I say is, this is node number 1 and this is node number 2, right? Let's say this is node number 3, 4, 5, 6 and so on, and I say that this is equal to I equals 1 over there, I equals 2 over there, then 3, then 4. Can you understand this thing? Right? So it means I am just having an index to define this position, this position, this position and this position. I say that I is the general index, I is the general node number, and node means this point. I would say this node is this point. Okay, these points are basically nodes. I would call them nodes. Now these are the indices. Now at this point or at this node I is equal to 1. At this point or at this node I is equal to 2. Similarly 3 and 4. Right? Previously I described it at x1 and x2. Now I am describing it through index. I would call this is known as index. Okay, I is the index. Now if I ask you find out value of the function at f2 at second node when you know the value at f1 at node 1, how I can write it? I would write it like this. Can you understand this thing? If you have any question you can ask. This is delta x. It means this is delta x. Sorry? No, this is x2 minus x1. What is this fy2? Basically it is f2, isn't it? What is this y1? This is the value of function at node 1. You understand that? Okay, so what was x2 minus x1? This was delta x. You understand that? So this is how you sorry? Exactly. This is just to define the position. It is just about giving the address of the delta x has something to do with the physical interpretation. This is x2 minus x1. So I2 minus I1 would always be like what? Right? So this is something which is physical. I am just changing the notation over there. I just want to describe that instead of saying that this is x1, this is x2, this is x3, what I am saying is this is index location 1, this is index location 2, right? So instead of saying that this is your house, I would say this is house number this, right? So that's how you introduce the indices, right? So technically this is index notation. Now this is how you proceed with the Taylor series. Now if I want to find out delta f by delta x from this formulation, can I write this delta f by delta x equals f2 minus f1 over delta x? I can write it like this, right? So you can say that I can approximate this partial f by partial x using this relationship. You understand that? Now partial f by partial x, f is some analytical function of x, but instead of finding that dependence in a functional form means you say that f of x is equal to x square. So what would be partial f by partial x? It would be 2x. It's the functional form. But instead of saying in these terms, I would say that partial f by partial x is f2 minus f1 divided by delta x. You understand that? So this is something which is known as numerical technique. Instead of having some values through a functional form, we are calculating the values by two distinct points, right? I don't know what is going on in between them. I just have 2 points, 1 and 2, and I say that okay, if I have this value at 1, I would have this value at 2. I don't know what is going on in between them. Okay, I can only know what is going on in between them if I know the functional form of the function. Okay, so this is how I would do that. Now if you look at this figure, can you see that? I hope it's very easy to look at that figure. Now just see it. Now this is just a 2-dimensional body. Just consider it a 2-dimensional plate of arbitrary shape, right? No problem at all. Okay, just look at that. Now how many points are there? Physical points are there on the plate? Infinite. Obviously infinite points. Now if I say I want to look at the temperature distribution on this plate, humanly it is not possible to calculate the temperature values at infinite points. Now what I can do, I can at least mark few points on the plate. I say that, okay fine, I would mark few points on the plate, and looking at the temperature on those certain points, I can say, okay, this is how temperature varies on the plate. That's how I can do that, right? Now my approximation would become better and better if I choose more and more points. If I choose less number of points, let's say if someone of you say that, okay, I would just place 10 temperature sensors on 10 different points, and I would say this is how temperature varies. And another person says, okay, I would put like 100 temperature sensors on the plate. Obviously his calculation would be much better, right? Similarly, if someone just put 1000 temperature sensors over there, his calculations would improve. But nobody can put infinite temperature sensors on that plate, right? So this is about placing the temperature sensors on the plate. This is just like that, okay? But there is a methodology. How do you mark those points on which you want to find out the temperature? Now what I can do is, in engineering, what you can do is, you can divide the whole geometry, the whole surface, within certain numbers of cells. Now these are small rectangles which you can see on that figure, small rectangles. So what you have seen is, you have divided the whole surface into small rectangles, okay? And those rectangles, those vertical and horizontal lines, they have few intersection points. These are the intersection points. Can you see that? Now these intersection points are the points where we are going to find out the temperature. You understand that, right? These intersection points are those points where the temperature is to be found out. You can find out temperature on these points, or you can find out temperature on the centers of these cells. Centers. Now you see, instead of finding out temperature in the functional form as a function of x and y, what you are doing? You are discretely measuring the temperature, at discrete points. This point, okay fine, then that point, then that point. Okay. Now division of the whole surface into small elements, this process is known as meshing. You might have heard about that, Gambit software and ICEM, CFD and ANSYS, right? Abacus, there are so many. So what you are trying to do with those softwares, before analyzing any kind of fluid flow or structural problem in ANSYS, what you do is, you always discretize the surface. This process is also known as discretization. I'm sorry. This process is also known as discretization. This division of the whole surface into small elements, this is known as meshing or discretization, right? So this is also known as grid generation. This is also known as grid generation. Now see, I say that, okay, this is my reference axis, x and y, because I am just talking about 2D plate now. This is x and y. Now these are the 2 points, let's say, where I am going to measure the temperature. These are the 2 points. Now this distance would be delta x, and I would say that this distance would be delta y. Okay, if over the whole surface delta x remains same and delta y remains same, it means between any 2 points, between two, you can say horizontal points, any 2 horizontal points, if delta x remains the same and between any 2 vertical points delta y remains the same, that grid is known as uniform grid. right? If delta x and delta y remains constant, they do not change their values over the whole grid, you would be having uniform grid. If those values are not the same between any 2 points, you have delta x at this between, let's say, point 1 and 2, and then between point 2 and 3 you have, let's say, some other value of delta x. It means you are talking about non-uniform grid. Okay, so this is how you can look at this thing. Now the point is, analytically, just analytically, or you can say the physical meaning of the gradient, if something is changing with respect to x and y, what would you try to find out? It's derivatives. Simple as that. It's derivatives, right? Now my point is, if you look at a steady state heat transfer phenomena in Cartesian coordinates, if you look at steady state heat transfer phenomena in Cartesian coordinates without any kind of heat generation, what would be the governing equation? We are still talking about conduction. Okay, so this is what this is: 2D steady state heat equation without heat source. Understood? Now, if you remember, I would not go into the details, mathematical details. I would just give you a small hint. For example, if I ask you how can I find out this value, partial t by partial x, I can write this t I plus 1 minus t I over delta x. You remember? T2 minus t1. You remember that? So now I am using a generalized notation, ti plus 1 minus ti divided by delta x. And what is the assumption behind this? I am assuming that I am talking about uniform grid. Delta x is not going to change. I am assuming that. Okay. Now similarly, for delta t over delta y, I would choose some other index. I would say this is tj plus 1 minus tj over delta y. You understand that? Now in this case, I am talking about this thing, like this is j plus 1 and this is j, and here I am just talking about this thing, this is I and this is I plus 1. Okay. Now you know that if you are talking about 2D steady state heat transfer phenomena, let's say this plate, let's assume that this is the plate, a very simple plate. I discretize this whole surface into small rectangular elements. You might have talked about that finite element methods and finite difference methods, and this is finite volume method. You would have a course in FEM as well, a very small course, an introductory course, and right. So this is something which you do, what you do over there. You always discretize the surface, and how do you approximate the values? This is the difference between all those techniques. You would have that flavor as well in your numerical analysis course, right? It could have been very easy to teach this thing if you have you would have taken the course on numerical analysis, but because you haven't, so I would just try to explain everything. If you have any question or any confusion, you can ask. You can just stop me and ask question. Now, what I have done is, I have taken this very rectangular plate, and I assume that I am just talking about uniform grid. What do you mean by uniform grid? Delta x and delta y remains the same all along the plate. Okay. Now here, just see, if I say that this whole line, this first line, you can say this is the first street, in a block. This first street has I index equals 1. Not sorry, I'm sorry. I would use I index for x axis and I would use j index for y axis. Let's say all along this line, I would say, because this is a horizontal line, y remains the same, isn't it? So this is another horizontal line, y remains the same, so I would say this is j index equals 2. Similarly, this line, y remains the same, so this is my next index in j. Similarly, this one is next index in j. Now this is vertical line where x remains the same. Okay, so I would say this is my I equals 1 over there, this is I equals 2, this is 3, this is 4, and this is 5. Okay, now that's how you can assign the indices. Now my point is, how many points are there, how many intersection nodes are there? 1, 2, 3, 4 and 5 over there, so there are 20 nodes. It means you need to place 20 temperature sensors over there. You understand that? Now looking at this thing, I would say that the grid size is 5 by 4. Grid size is 5 by 4. This 5 represents the maximum I index and 4 represents the maximum j index. So how many total nodes would be there? 20. Sorry? Okay, still if you want to find out there, let's say this value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can do that as well. Now it depends on whether you are going for finite difference, finite volume, finite element. So again, there is a discrimination, right? I would not go into that detail, but I am just telling you, if you go for the computation at the center, so then how many nodes are there? You have 12. In that case, your grid node would be like what? Right? So these are what cell-centered schemes, you can say, right? Few are like nodal schemes, and then you have cell-centered schemes. Sorry? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then those 5, 20. Okay, I would talk about that. Just let me complete that. Now, what's the point in there? It is a Laplace equation, second order in x, second order in y. So you need to have 4 boundary conditions. So you know the temperature at this surface, you know the temperature over there, you know the temperature over there, and then over there as well. So even if you go for the computation of temperature at the nodes, how many unknown nodes would be there? Come on, all the nodes on the boundaries, you know the values. 1, 2, 3, 4, 5, 6. You understand that? You need to know those values on the boundaries. You can't solve that partial differential equations if you do not know the boundary condition. No, you should know the values of the at the boundaries. You should know the boundary conditions, isn't it? To solve the PDE, you should know that, isn't it? It is second order in x, second order in y. So you should know 4 boundary conditions at least. Right? Now, I suppose that you know how to give the indices. Let's say, if I ask you what is the index of this point, this one, this is 3, 2. So I can say that this node would be having an index of 3, 2. So this first index would be describing I and the second index would be describing j. Clear? Now, this is quite interesting. Now, just remember those indices and how you define them. Let me choose a case over there. Now, for this class, I would use those centers to find out the values. Those centers. although you can go for the finite difference scheme as well, you would have the same result, same formulation of the equations, but I would go for this cell centered energy balance method. Okay, now just look at this one. I choose this section and separate it from the rest of the body. I just choose this section, okay, this green lined section. Now just those 5 cells, I have picked those 5 cells. Okay, I want to use the values on their centers, and this is where I am going to talk about energy balance method. Now just see, for example, if I say this index is I comma j, what would be this index? I plus 1 comma, what would be this index? What would be this one? I comma, and this would be I minus j. So you know at least how to place the indices. You understand that? Now, instead of looking at it from that finite difference or Taylor series point of view, we would look at it as if we are just balancing the energy in each cell. In each cell, right? Now see, if you look at this cell, so just treat it as a control volume. Just treat this cell, this center cell in the center, that is basically just treat it as a finite control volume. I can say that whether the energy would be coming in or the energy would be going out or the energy is being generated within that cell. That's what I can say, isn't it? Because we are just talking about steady state phenomena, so we are not going to talk about the storage of energy. Okay, if you look at the unsteady phenomena, obviously you can talk about that storage term as well. There are 4 terms, if you remember, for energy balance, right? Energy which is coming in, energy which is going out, energy which is being generated. And if you talk about the unsteady, then you would have energy which is being stored. Now we are talking about steady state case, so we have only okay, so this is what I can say about this thing, that there is a control volume. It has 4 neighbors, upside down, right, left. Okay, now upper and lower cells, they may basically transfer heat to that cell, right, to that cell. I can say that from its neighbors, either the energy is going in, just like that, and let's say rest of the 2 cells may have energy transferred from the cell at the center. Okay, this is how it can be pursued. Let's say for to make the case very simple, I am not going to consider the energy generation at this point, although you can consider that, but I am not going to consider any kind of energy generation. Now if you look at this thing, let's say this heat transfer rate is Q1, this heat transfer rate is Q2, this is Q3, and this is Q4. If I ask you, apply the energy balance method on this heat transfer phenomena, conduction phenomena, you would say, okay, fine, Q1 plus Q2 minus Q3 minus Q4 should be equal to 0. That's what we would say, right? Energy in is equal to energy out. Very simple. Now see, what does that mean? This Q1 is what? If you remember, this is for conduction, isn't it? You are talking about heat transfer within the same medium. So this is conduction. How can you define that Q dot for conduction? Fourier law. So you can define it like K A partial T by partial This should be x. Why? Because heat is being transferred in the x direction. Let's say if I ask, no, I'm sorry, this is Q1. So this is Qy, I'm sorry for that. This is heat transfer in the y direction. Let's talk about Q2. Okay, put that negative sign. Okay, so now then you would have minus Ka partial T by partial x. You understand that? Similarly, Q3 would be minus Ka partial T by partial x. Q4 would be, I'm sorry, this is just, you understand that this is Q1 dot, Q2 dot and all that. This is heat transfer rate. So then you would have minus Ka partial T by partial y. Is that clear? Now you see, we keep the cell where the temperature is to be known, where the temperature is to be known. I want to find out temperature at this ij location, right? I assume that there are four, not assume, basically I have discretized the whole surface. I say that, okay, there are 4 neighbors. From those 4 neighbors, 2 are transferring heat to that cell and 2 are basically getting heat from that cell. Okay, so if I apply the energy balance method on that particular cell where the temperature is to be known, energy in needs to be equal to energy which is going out. So this is how you can write it. Now let me talk about this term, this term. I can write this Q1 as, just be very careful, this is very important to understand that. This is minus K and then you would have some area term, and can I write this partial T by partial Y as Tij minus j plus 1 minus Tij. Now see, heat is being transferred from where to where? Here to here. You understand that? So this is T1 and this is T2. So I would say that this is just being multiplied over it because I don't have space over there. Let me write it over there. So this Q1 would be equal to minus K. There would be some area term and then I can write it as Tij plus 1. This is the index of this node, minus Tij divided by delta Y. Now what should be the area? Now this heat flux is normal to this surface, isn't it? This is kind of a control surface. Those boundaries, cell boundaries, these are just like control surfaces. So if I say what is the area of this control surface, this is basically delta x and some protrusion which is going out of the plane, isn't it? Which is coming out of the plane. So I assume that for 2D it is just 1, that protrusion is 1 unit, right? So I can say that this is delta x into right. Now similarly for Q2, just see, for Q2 what can you say? This is minus K. What is area? Delta Y into 1. So this is delta Y into 1 and then it is going from where to where? Here to here. So this I can write as Ti what? Sorry, Ti minus 1 J minus Tij over what? Delta x. You remember I wrote those relations for delta T by delta x and delta T by delta y from which expression? That Taylor series. Okay, that Taylor series. Okay, so now let's say similarly I can write down this Q3 term, Q dot 3 term as minus K delta y into 1 because it is going out. So I would say this is Ti comma j minus Ti plus 1 comma j over delta x. Similarly Q4 is equal to minus K delta x into 1. You know how to calculate that area, I have already explained it. So then you would have, because heat is going from here to here, so it would be Tij minus Tij minus 1 over delta y. Now at least you have Q1, Q2, Q3 and Q4. And what was your actual equation? Sorry? You are talking about this Q4? So this Q4 is going from Ij to Ij minus 1, because it is lower than J, right? So this is J minus 1. If you talk about this thing, this was what Q1 is. Q1. Okay, just look at that. What is the difference? Is it vertical? What is the gap? What is the orientation of the gap? Is it vertical or horizontal? It's vertical, right? So for Q2 and Q3 the gap is horizontal. You understand that? So you just need to look at the orientation of the gap, whether it is vertical or horizontal. Is that clear? So now I would just use all those expressions, those 4 expressions, and put them back into this equation, this one. Okay, and then simplify it. How much time we are left with? Okay, 5 minutes, we can do that. So this is Q1 plus Q2, please, minus Q3 minus Q4 equals 0. Put those dots yourself. Now this Q1 was, because K is the same, this K remains the same in all the equations. So I would just keep K out of it with minus sign, minus sign, and then I have delta x. I am skipping that delta 1.1 portion. Tij plus 1 minus Tij, and obviously this is being divided by delta y. And then next I have Q2 term, where I have delta y over delta x, and then I have Ti minus 1 j minus Tij. Similarly, next level I have this negative sign with me. So I'm sorry, if this is negative, this should be positive. Okay, fine, then a negative sign is there. I would have delta y over delta x and Tij minus Ti plus 1 j, and then finally I would have delta x over delta y Tij minus Tij minus 1 equals 0. So this is the expression which I would get out of it. Okay, now see, I can simplify them. Let's say this is delta x over delta y equals beta. Just to simplify the expression, this is basically beta, right? Now this k cannot be 0, so it means this whole expression inside the brackets needs to be 0. Okay, so I can write it as beta into Tij plus 1 minus Tij plus 1 over beta Ti minus 1j minus Tij minus 1 over beta Tij minus Ti plus 1j minus beta Tij minus Tij minus 1. Okay, now just simplify this term. On the left hand side you should only have Tij. and just take all the rest of the terms on the right hand side. Right, on the left hand side you should have only Tij. This was what you need to know, right, and put all the rest of the terms on the right hand side. Now all the rest of the terms on the right hand side would be having Ti minus 1j, Ti plus 1j, Tij plus 1 and Tij minus 1. Right, now see, and obviously there would be some multiplication factors of beta. Let's say some beta plus 1 over beta would be there. Now it means you can only find out this Tij if you know all the surrounding values, isn't it? You can only know this Tij if you know all the surrounding values at I plus 1, j, I minus 1 j, ij plus 1, ij minus 1, right? You can only know that. Now this is how you proceed. This is how you proceed with the numerical technique. Just look at the very first figure. You know the values on those points, isn't it? Now if you know the values on these points, you have some information to find out the value over there. How? I would do that in the next class, right? But starting from the boundary, you see, you know the values at the boundary, and at least you have some points where you know the values and you can find out the adjacent values through that information. Okay, how you do that? Let's do it in the next class.